Hello. Today we'll take a look at the bipolar PI circuit from ITMD3, also known as the Pulse5 circuit. First, let's take a look at just the blank PCB. It's 6 inches, 150 millimeters by 4 inches, 100 millimeters. It's double-sided. I actually bought these boards from JLC. And almost all the components on here are through-hole. The only exception are some 0805 capacitors on the back side. These are power supply bypassing capacitors. They help with power supply noise. If you omit them, the circuit will still work. So they're not critically necessary, but they do help. I try to mark everything on here on the silt screen. For example, test points, and of course all of the component names and so forth. On this version, I did forget to mark the power supply polarity. Positive is on the right, negative is on the left, and also I usually mark the range of voltage or the anticipated voltage. On this design, you can run probably a minimum of 9 volts and probably a maximum of around 18 volts. So here is the built PCB. You'll notice that all of the ICs are socketed. I do that for 2 reasons. Easy replacement in case, for example, I want to use a different preamp. Or if I burn up a part, but also for easy reuse. You know, this is Rev 2.1, so there was a Rev 1.0, a Rev 2.0, and so I pull out all the chips and I reuse them in the next revision. Saves money. Most of the passive elements, if you sort of look at this at an angle, most of the passive elements are elevated off the board. Again, that's for easy removal in case I want to try different values. The damping resistor here and the two input clamp resistors for the preamp are all socketed, and the reason for that is that I was adjusting the values, playing with the values, so that makes it easy to swap values in and out. For bench testing, I've got the delay and the TX frequency pots on regular potentiometers wired into the board. For all the other pots, I'm using trim pots. You know, we have gain, ground balance, threshold, and volume. And then the coil plugs in here, and the board is set up to use a separate transmit and receive coil. For this demonstration, I'm using a mono coil, so I don't have a receive coil to put on here. And to deal with that, I've just shorted the receive to the transmit, and that way I can run a mono coil that automatically feeds into the receive. If you were to really build a detector to use both a mono coil and say a double D, you would put these shorts in the connector of the coil itself. You wouldn't do it here. So that, I believe, covers the basic board. And in the next part, we'll look at some waveforms. I've got the TX drive waveforms on the screen, and right now the pulse width is 50 microseconds, which corresponds to a half TX frequency of 2000 Hertz. You can see here on the screen we're at 2000 Hertz for the yellow waveform, which is half the pulse. So we have alternating pulses plus, minus, plus, minus, plus, minus. So the overall pulse frequency is 4,000 hertz in this case. And the power consumption is about 1.5 watts. That's at 10 volts. So let's increase the pulse width to a maximum of 300 microseconds, and let's adjust this out just a little bit. And okay, now we're at a pulse width of 300 microseconds and a half frequency of 330 hertz. So the overall pulse frequency is 660 hertz. So in this case, we have a narrow pulse width, higher frequency. That's probably good for small gold targets. And in this case, we have a wider pulse width, lower frequency, and that's might be better for deep silver, for example. In the low frequency wide pulse width, the power consumption is 2.5 watts, which is higher. You know, the 50 microsecond case is 1.5 watts, but it's still reasonable. And it is possible to scale the TX pulse width and frequency in firmware so that power is constant. It's a nonlinear relation. I didn't do that, but it wouldn't be difficult to do. Now keep in mind that power consumption is converted to heat somewhere. In this case, it's mostly the damping resistor and the input clamp resistors, so be sure to size them accordingly. There is a caveat on the PC board. This is the damping resistor, and I really didn't give it enough room here. It needs to be a bigger resistor, and there's room to make it bigger. And that's one thing I'll do if I do a board revision. Okay, so let's now turn on the third channel and see the preamp signal in magenta. And let's take it back down to the minimum and zoom in and see what the settling is. So this is the final saturation point here, and it comes out of saturation. It looks like about 12 microseconds, and after that the preamp looks fairly linear. Might be slew rate limited here, hard to say. If you look at a target, say the US nickel, you can see waveform motion all the way down to the saturation point. So that's what you want to look for. And here's a high conductor silver, and you can see motion farther out with that. So it appears to come out of saturation at 12 microseconds. However, if you look at this little glitch in the transmit waveform, and I'm going to take the ground off of the preamp signal, and now you see the same glitch in the preamp signal. That is actually where the H-bridge is switching. And so if you were to look at the actual flyback, let's turn on channel 4 and let's take that way down, and we look at, there's the flyback signal for the transmitter. You can see that the flyback occurs where these glitches are at. So in reality, we can back this up a little bit, and now we have put the actual transition in the middle of the screen, and now it looks like about 10 microseconds is where the preamp actually comes out of saturation. There's about a 1.5 microsecond delay between the PIC pulse that we're probing and the actual H-bridge switching. Even 10 microseconds coming out of saturation isn't especially fast. But I'm using a coil right now that's almost 500 microhenries, and you can do better with a faster coil. The reason I'm using this coil is that all of my fast coils are made for monopolar pulse systems, and one side of the transmit coil is connected to the coil shield. You can't do that on a bipolar design. You have to connect the shield on a separate third line and not connect it to either side of the transmit coil. So that's important to keep in mind. Let's now add one of the sample pulses. So I'm going to disconnect this from the flyback, connect it to the sample pulse, the target sample pulse, and let's center that back. Well, let's move it down a little bit so we can actually see it. And we can see that the sample pulse starts at about 12.5 microseconds. And that's just past the point where the preamp comes out of saturation. And that's important. You want to make sure that the sample pulse never gets backed up into the saturation point of the preamp. That just adds offset to the demodulator and wastes signal. So we have about 12.5 microseconds, and we can use the potentiometer for the pulse delay to vary this, like so. And let's get rid of that. And so now we can adjust the pulse width from about 12.5 microseconds to about 28 microseconds. So that's our sample delay range. And the range is easy to alter in code. So if you end up with a fast coil that settles below 10 microseconds, in code you can pretty easily either shift the range of the sample delay or extend the range of the sample delay if you want. Next, let's move the preamp probe over to the ground sample pulse. And we'll reduce the amplitude here. Move this down a little bit, like so. And change our time scale. Okay, so, well, let's stop there. Now we see the target sample pulse, the ground sample pulse, and if we change the sample delay, both pulses move together in unison, as they should. Now, if you play with timing on this, especially the sample frequency, you want to make sure you always have enough RX time, and that's the time from the end of a pulse to the beginning of the next pulse. So in this case, we're at about 200 microseconds of RX time. You want to make sure you have enough RX time for both of these samples, and a little bit of room left over. In this case, we could clearly increase the frequency even higher than 4 kilohertz. However, that does also increase the power consumption. We can also see that if we alter the frequency, the sample, the target sample and the ground sample stay in the same place because they're relative to the falling edge of this pulse. There is, of course, another set of target and ground samples after this pulse, but with opposite polarity. They're on the negative polarity of the receive channel. Now let's take the target sample and move it over to the B clock line. Now the B clock line is the pulse from the microcontroller that drives the charge pump. And in this case, we see that there is a complete B clock cycle for every pulse. So for this pulse, we have a complete cycle. For this pulse, we have a complete cycle, and so forth. So at the highest frequency, in this case 4 kilohertz, the charge pump is also running at 4 kilohertz. And if we slow down the transmit frequency, the charge pump clock also slows down. We want to make sure that we don't run the charge pump too slow. So I'm going to take the target sample probe and move it over to the charge pump output. Let's recenter this to 0 and expand this. And what we see right now on channel 4, which is the charge pump output, this is the analog voltage output, it's at about -8 volts for 4 kilohertz. As we decrease the transmit frequency, what you see is that the charge pump output starts collapsing. It's at 660 hertz, it's now at -7 volts. And so it is more efficient for high frequency, less efficient for low frequency, and if you keep going lower, this voltage will continue to collapse until the charge pump stops working and you lose the VEE power domain, the -5 volts. So if you want to run the circuit lower than, say, 660 hertz is minimum right now, you might need to drive the charge pump differently. Before we leave the O-scope, I want to show the output of the demodulators. So I'm going to move channel 3 and channel 4 off of the charge pump and onto the demodulator outputs. The magenta channel, let's zoom in. Wrong one. Let's zoom in. We'll do 1 volt here and 1 volt here per division. The magenta channel is the target channel and the blue is the ground channel. And what we can see, just looking at targets again, is that a low conductor primarily moves the target channel, not much happening with the ground channel. A high conductor moves both channels together. But the problem I'm seeing is actually with this glitching going on here. And this is something that I don't normally see using 4066 type switches. And I think it might be due to the 4316 switches, I'm not sure. If you zoom back out and look at the demodulators, they otherwise seem to be fine. It's just, and it's primarily on the target channel, although the ground channel does it as well, but primarily on the target channel you get this big glitch going on. The problem with this is the glitch carries on through the amplifiers, the ground balance, and all the way to the audio. And this creates a little bit of noise on the audio. It's especially noticeable at low volume. Again, I don't know exactly what's going on there. I haven't tried to troubleshoot it, but if you look at the ground balance signal, which is now the blue signal, let's turn this one off. So there's the ground balance signal. You can still see the glitch in the signal, and you know, just looking at low conductor target, it's going to go down and then bounce back. And looking at a high conductor target is going to go up and then bounce back. So that's what the signals should look like, except for the minor amount of glitch. I just wanted to bring this up as a potential issue. I would like to know exactly what's going on, but I haven't had time to dig into it. Maybe someone else will be able to figure this out. It's been quiet so far. So now we'll plug in the speaker, turn it on, and I can adjust the threshold and the volume for a reasonable idle tone, but for the purposes of the video, I'll keep it really loud. So I have a US nickel for a low conductor, and the low conductor response sounds like this. You can hear as you get closer, you get a high tone followed by a low tone. High, low, high, low. Same thing, sweeping. For a high conductor, I have a US quarter, silver, and we get a low, high, low, high, low, high. Same thing sweeping. A nail also does a low high. Of course, if you turn the nail long ways, you get a double response, typical of any detector. The one thing I don't like about this circuit is that the 555 oscillator is really limited in its frequency range. I mean, you can hear the difference between the high-low is not all that great, and it doesn't give you the wee-woo sound of the MindLab, for example, but it demonstrates the concept. And you can replace the 555 VCO with a better VCO. One that I like is the relaxation oscillator, such as the one used in the TR discrimination circuit in ITMD3. Now, that's not a VCO, it's just a relaxation oscillator run at a fixed frequency, but you can add some components around it, make it into a VCO, and the way to do that is really just a Google search away. It's well documented how to make a VCO out of a relaxation oscillator. So let's do a demonstration of the ground balance. So right now we're pretty well ground balanced. Hardly any response to that rock. Very little response to that rock. So what I'm going to do first is I'm going to adjust the ground balance too low. Now let's do this. And when the ground balance is too low, the hot rock gives a positive response as you're getting closer. If you let it retune, then when you pull the hot rock away, you get a negative response. But it's positive, negative, positive, negative. And if you sweep the hot rock, it sounds like a positive response. Same thing with the big hot rock. This one's not quite as strong. It's bigger, but it's not as strong a hot rock as this one is. Okay, so now let's adjust the ground balance to high. And one of the things I notice on this circuit is, as you're adjusting the ground balance, the volume is changing or the threshold is changing. I suspect that's maybe an issue with an offset, one of the op amp offsets or something. I'm not sure. It really shouldn't do that, but I haven't explored what's going on. So now the ground balance is too high, and the hot rod gives a negative response as you get closer and a positive response as you pull away. So that's opposite of what we were getting before. And you can get the same thing with the big one. And so what we want to do is adjust it until we get no response. It's a little bit positive. That's pretty close. Okay, we're ground balanced again. And again, low conductor, high conductor, iron. Okay, I think that's all I have to say about this. Now keep in mind that the designs presented in ITMD are primarily for teaching concepts. In most cases, including this circuit, they're greatly simplified to focus on the concepts. They're not intended to be polished designs ready to take out hunting in the field, but rather as a starting point for a better design. So I've even pointed out some drawbacks in this circuit that probably need some improvements. So that's up to you guys to figure out how you want to do that. But the circuit does demonstrate everything you need to know about bipolar PI and ground balancing. Now finally, you're welcome to post feedback below on YouTube, but if you have questions about the circuit, it's best to post them in the Geotech forums where I'm more likely to see them and can give a better response. You know, I can post drawings, pictures, and other things, whereas on YouTube I can type in some text and that's about it. Okay, that's it for the bipolar circuit. Thank you.